How's it going, everybody? Thanks for having us out here at OffensiveCon. We're excited to be here. It's our second year of the con and our second year presenting, so we're excited to share with you some new stuff about exactly how hard it is. Our talk is Bugs So Nice They Patched Them Twice, a continuing story of failed patches. And specifically, we're going to be looking at what is going on in Adobe Reader and Adobe Acrobat. It's one of our new favorite products. We've been following it now for a good amount of time, trying to understand exactly why we're receiving bugs twice from researchers out there in the world, and kind of getting an understanding of how well Adobe is actually patching their software and how much time and effort they're actually looking at the actual root cause of the bug itself. So we're going to be talking across the architecture of the application itself, looking specifically now at the JavaScript APIs. We'll be looking at the XSLT engine. We'll be looking at indexing, and we'll be looking at file parsing. So we're not talking about just one specific area in the application, but the actual, what seems to be widespread misses as it relates to patching vulnerabilities. So a quick first introduction. My name is Brian Gorenc. I'm the Director of Vulnerability Research inside of Trend Micro. My primary responsibility is running the Zero Day Initiative program, which is the world's largest vendor-agnostic bug bounty program. So there's probably quite a few people in this room that we've purchased bugs from before, but we work with researchers. When they find 0 days, we purchase them and work with the vendors to get them fixed, and we release protections for those bugs while we do it. I also organize the Pondo and Hacking Contest, which is happening here in March. Working with here Jazel.
All right, I'm Jazel Spelman, or Wandering Glitch, and I've been part of ZDI for just shy of 7 years. I very much like static analysis, and that's generally what I try and focus on. And I'm going to pass it over to Jewel. But one thing about him that he probably won't like to admit is internally, because he spends so much time on Adobe, we usually refer to him as Adobel.
Yeah, that's true. So I'm Abdul. I've been working with the ZDI for the past 6 years. I'm also the case lead, so basically any case that gets in the program, I dispatch it to the analysts, and I end up pricing the case. I also do a lot of root cause analysis, research, and stuff like that. So if you guys have any questions on the pricings, which probably a lot of you do, so you guys can bribe me outside. I can probably fix that for you guys.
I didn't hear that. All right. So just kind of quick overview to level set everybody. If you haven't spent a lot of time looking at Adobe products before, this whole presentation is about Adobe Acrobat and Adobe Reader. It's been around since 1993, and it's very widely deployed. In fact, I get to talk to customers who are deploying these, security solutions for our company, and routinely that is the software of choice for PDF, PDF stuff. If they're not using that, they're using Foxit, right? One of those two. What's nice about Adobe is it's multi-platform. So from an attacker's perspective, you can actually, take the bugs that you're finding and lay them across different architectures. So that's really makes it an interesting target to look at. And there's a lot of old code in there. Right, so we'll be talking a lot about the details of the architecture, and some of this stuff is open source code that's no longer maintained. Some of it's stuff they purchased from third parties. Some of it's stuff that they just don't actively maintain very much because there's not a lot of feature change in it. So there's a lot of old code in this product that you can go look at and reach from from basically a PDF document. So it makes it a fully featured, very rich, very juicy attack surface for people, and we're seeing a lot of that come into the program now. So if we look at the architecture, there's really 3 different components that you kind of want to be aware of. First is the core Acrobat DLL or acroread32.dll. And from there, you can actually load in different plugins based on the functionality that you're trying to trigger inside of Adobe Reader or Adobe Acrobat. So you can look there, eScript, and a bunch of different plugins that you can pull in and start activating stuff. And they actually have access to these back-end DLLs, which you can then go and kind of execute a lot of the functionality here in the back end of the application. And that's where a lot of the older code exists, right? So that's where you're going to eventually want your POCs, your exploits to be hitting. Now, we sit there and we kind of look across the ecosystem, and we're buying vulnerabilities from lots of people from all over the world, so we kind of get an idea of what's happening and when things are becoming hot in specific applications. And so back before 2015, Adobe Reader, and at least in our program, wasn't receiving a lot of attention, right? So we did some research, and we released some research in 2015 that kind of spawned some people to actually start submitting vulnerabilities in Adobe Reader into our program, and it's really blossomed since then. So you can see back in 2015, what's depicted on the slide is the patched bugs that have come from ZDI in Adobe Reader over the years, right? So 2015, less than 100 bugs. And here in 2018, almost 250 zero days that were submitted and purchased by us and patched. Now, we kind of look at those bugs as they're coming in and we try to like analyze for trends, right? That's kind of what our job is. And so what we want to do is understand why the bugs are manifesting in the way that they are, right? And what we noticed, in 2017, 2018, is that a lot of the bugs that we were receiving were just basic bypasses for the bugs that we had purchased in the previous years. Right? So, like we're paying twice now for these bugs, like what the heck's going on? And so, we wanted to kind of analyze that a little bit more, and we continue to watch this trend happen, and that's why we're talking here today. We want to show you the actual code, the actual fixes, and the proof of concepts and the bypasses for this proof of concepts so that you can understand and look at those bugs yourself, generate proof of concepts, and maybe find your own bugs based off of bugs that are previously patched. Now, we're not the only ones who noticed this. In fact, this is some conversation that was happening around the time that the hacking team breach occurred with Vitaly Torpov talking to, and I quote, it says, Adobe analysts are awful and they're unable to extrapolate, right? And, basically what he's saying is that when they get a patch, they're not actually looking beyond the patch itself, right? As a security researcher or security analyst, you want to, you hope that the researcher takes your bug and they look at it and they apply it across the entire software, try to fix a lot of bugs, especially if you're on the white hat side of the market. That's what you want to happen. But in this case, even not that, most of the industry is now starting to notice that that they're missing bugs. And I know Jazel had a story here where he wanted to talk about, an experience like this.
So around the same time, it was either 2015, maybe 2016, there was a vulnerability that Project Zero had reported in JPEG 2000 parsing. And it was a stack buffer overflow, and there's an if-else clause. In the if clause, if when true, there's potential stack buffer overflow. Adobe patched it, and Tencent looked at it and ended up taking advantage of another bug that's right next to it and use it in Pwn2Own. And the kind of funny but really just sad thing is it was in the else clause, almost the exact same stack buffer overflow. They fixed it in the if branch, but not the else branch. And that's just a great example of how they very much focus on breaking the crasher and not really looking any further than that.
Yeah. So we're going to go over a set of failures, right? We're going to be looking at JavaScript, we're going to be looking at XSLT, we're going to be looking at indexing, and we're going to be looking at file parsing inside of Adobe Reader. And the way that these sections work is we're going to give you a little bit of overview of what is actually happening in that attack surface, how you would go about hitting it, what a proof of concept looks like. We'll talk about the vulnerability in question that we're looking at, and we'll talk about how it was triggered. We'll talk about how exactly they patched it the first time. Then we'll talk about how easy it was to bypass and how fast that happened. And then we'll talk about how they actually fixed the core issue. So when we look at JavaScript API, these are the components in the architecture that you can hit. So from AcroRead 32, from the core, effectively, you can actually force the loading of the eScript plugin. And from the eScript plugin, you can reach basically every subcomponent in the backend that you want to reach, right? So it's a very powerful way of accessing a lot of the old code that's in the back there. XSLSE being the XSLT engine, JPEG parsing, a bunch of different stuff that you can reach from JavaScript, which makes it a very interesting place to start if you're going to attack Adobe Reader, Adobe Acrobat. Now, obviously, everybody, if you haven't been in computing for, basically 5 minutes, you'll know about JavaScript. And what's interesting about Adobe's is they have a bunch of JavaScript APIs that they've developed specifically for manipulating the actual PDF itself and making it interactive. Things related to forms, JavaScript APIs for forms, annotations, collaborations, et cetera. Like that document is like 300 pages long, right? So there's a lot of documentation and a lot of stuff going on there for you to interact with. Now, the JavaScript engine itself is actually a spinner spider monkey, so if you've been looking at that engine, that's what it is. It's all contained in eScript API. And a lot of the documentation, though there is a lot of documentation, it's actually not all of the features of the JavaScript engine are actually documented. And so a lot of them are undocumented, and you can actually use some of the stuff that we've talked about in other presentations related to Adobe Reader to actually find all of the undocumented APIs, and some of the bugs that you're going to be able to uncover are in places that people didn't know actually existed, right? So there's an example of collaboration where the documentation says there's 3 APIs off of that object, but in reality there's like 130, right? So at one point there was. And some of the APIs are only available for the standard or professional versions of the product. So obviously, if you're going to be targeting somebody, you're going to want to know what they're using. And so it gives you an idea of what's available to attack. Now, Adobe's JavaScript runs in two contexts, and Abdul is going to describe a little bit about what those contexts mean.
So in the JavaScript API, there's two contexts, privileged and non-privileged. So if you guys go to the API reference that Adobe provided, you would notice that there's an S, like a red S, next to certain APIs, and these APIs are considered restricted or privileged. The non-privileged APIs can be executed from normal document privileges. So if you open a PDF, you can execute these APIs, no problem. And all these APIs have been really hardly audited and looked at. So most of the bugs that you guys have seen in public are definitely bugs targeting these non-privileged APIs. Nevertheless, the privileged APIs can be executed from inside a doc context if they're inside a trusted function and they're being wrapped in a block like a begin priv block and end priv block. These APIs have not been properly audited and have not been looked at. For the one reason is that basically it's really hard to hit them, and it would actually require you a privileged API bypass in order to hit these. So you basically have to chain multiple bugs together to hit them. That's basically all I have to say about this slide.
Yep. And we do believe that there's quite a few like use after freeze and things back in those privileged APIs. So if you can figure out how to do the JavaScript API restriction bypasses, you can hit a lot of those bugs, and those are very valuable now.
In fact, there was a bug that I found in a privileged API, which is very simple. It's called launch URL, the API, and basically on the macOS version of Acrobat, it was vulnerable to command injection. So basically, if you give it a path of an actual binary on disk, then it's going to execute it. So that's how much it hasn't been audited. No one touched it before.
Okay. All right. So the first place we're going to look a little bit is annotations, right? So annotations are used to create interactive forms and multimedia inside the PDF itself. And the APIs are relatively simple. You can see just add a knot or get a knot or get a knots. You know, there's different APIs that are available, basically allowing you to create that interactive PDF that you want to have, right? That's the whole point of the PDF. But when we took a look at this attack surface, one of the things that one of the kind of earliest veins of gold that we found in Adobe Reader was basically finding ways to force the document object to be freed. And the first way we figured out how to do that was using CloseDoc, right? CloseDoc API, right? So the proof of concept here, CVE 2016-0931, is a bug that I found when we were doing an audit of this. And we had discovered that in this case, the structure of the proof of concept is you define an array, you define a getter off of the array for the first element in the array, and in the getter handler, you basically just close the doc. And then basically any API that you call later, when it handles the getter, it's going to remove the document object and force a use after free condition, right? So this is the simple proof of concept that we developed back then. And it was so effective that I remember we were sitting at Recon, we had figured this out, and we were literally sitting in the conference room there at Recon, going line by line through the API document, and we had discovered like dozens and dozens of bugs just sitting there at the conference using this technique, and just not even like fuzzing, we just taking the document and going through it. So we said, okay, well, we're gonna go fix this issue with Adobe, so we disclosed all those bugs to Adobe, and they fixed the bugs, and we kind of, said, okay, well, that's that, right? We're going to move on. We're going to find something else. And we decided, let's take a closer look at finding other ways where we can close a document. And this is what we came up with. Right? Literally the same exact thing, except just with a different way of closing the document. So very highly effective. We found that like literally a couple days after the patch went out. And again, we went line by line through the API document, ripping it apart, and finding tons and tons of bugs, just looking for different ways of closing the document, right? So you think that they would have, tried to take a little bit deeper approach, just not like looking at the proof of concept itself and trying to stop that, but trying to figure out the core of the issue itself. Now, the way we're going to look at like the real bugs that we're going to analyze here, the first bug is this is an OCG set intent heap-based buffer overflow. The original bug was CVE 2018-4910, and it was ultimately fixed in CVE 2018-4962. Right? So What is OCG? So OCG is optional content groups. And so when you want to have if you think about like a CAD drawing and it's got different layers to show different things, that's effectively what OCG is for Adobe. It controls the visibility of page content. So if you want to have a multi-language document, you can have a page or a layer that's English and a layer that's German, right? And so you can toggle those on and off with flags. And you can all do it from JavaScript. So there's a nice set of APIs that are available to you. And the one that we're looking at specifically here is set intent. Right? So set intent is supposed to set the intent array for the OCG objects, and it basically takes an array, right? So if we look at the core bug, it's the classic integer overflow leading to a heap-based buffer overflow, almost like stuff textbook from some of the C programming guys back in the day. So what ends up happening is in the vulnerability, they get the length property right here, fully controlled by the attacker. Then they do a little bit of math, multiplying it by 2, which wraps the integer to make it small. Then they call malloc on that to create a small heap object. Then they start using a loop, start going into a loop with the length that was provided previously, and then it ends up resulting in a heap-based buffer overflow, right? Classic, programming mistake being made in this example, right? So how do you trigger the bug, right? So let's take a look at the proof of concepts. Now the CNT doesn't really matter, but what's important is that there's an array there, and there's a new getter. We're defining a getter that basically sets the length of the array to a value that is going to wrap. So in this case, 7ff. Then you're going to call set intent on that array, and it's going to result in the heap-based buffer overflow occurring. Now, we sent this to Adobe, sent this proof of concept to Adobe, and they released quarterly, so it took them months to analyze this bug. They had months to look at it. And so you would think, like an integer overflow, you're going to do some sort of overflow calculation, overflow check to make sure that you're actually, correctly fixing the bug. But no, this is what they released, which is effectively only looking
It's still a quick fix.
Yeah, it's a fix. It's a fix. It's a fix. You can imagine the guy was probably under a lot of pressure, or the guy or the gal under a lot of pressure to get the fix out. So this is what we had, right? This is what we get back. Yeah, it's quality. All right. So you think about, okay, obviously, this patch is bypassable, and what's kind of funny because we know people look at our advisories and they know that the bugs are coming out, and we know that people monitor all that stuff, right? And so when the patch came out, the researcher literally sent us the bypass in like an hour after the patch was released. So like immediately into the system, we had a brand new proof of concept that was triggering the bug again. And this is exactly what the proof of concept looked like. So quite good, yeah, very enjoyable. We paid him twice, so so yeah. When I'm working on budget, I got to account for all of these things, So later on, Adobe figured out how to do math, and they fixed the vulnerability, made sure that the length wouldn't wrap anymore, and as a result, the calculation would work. So. That's the JavaScript API section. I'm going to turn it over to Jazel. He's going to do the XSLT section and talk about that area.
All right, so extensible style sheet language transformations, XSLT. If you're ever in the unfortunate position of having to process XML at all, but especially large quantities, XSLT is a great way of just transforming that data. I'm going to give a little bit of an overview of it, but in Adobe Reader or Acrobat, you start off with Acrobat or AcroRead 32 as you would with anything else. You have two vectors in. You have eScript, so through JavaScript, and then you have Acroform, which is like XML forms architecture. I'm not really going to cover that as much, though one of the bypasses will use that. Ultimately, though, it ends up going to AXSLE, which, as Brian said earlier, is the XSLT parser. All of that code is really just based on, and really is, a open source product called Sabletron that was abandoned, I think, in 2010. The version that Adobe is currently using in the reader that's shipping right now is a slightly modified version in that they've had some spot fixes, but as we'll see, they don't fix everything perfectly. One of the first bugs we found, or we had submitted to us, was in 2012 by Nicholas Gregoire, who often goes by Agari. And he broke the patch and resubmitted a case in 2017. All right, so here's just an example of what using XSLT from JavaScript in Reader might look like, or from a PDF might look like. We have this very, very simple XML document where we just have a self-terminating node, nothing too interesting. We then have an XSLT, which is also just XML. In this case, it's going to match some stuff and then run for each for every node that it runs, and then just sorts it. As far as actually using the API, it's fairly straightforward. We parse our XML, and we end up with a DOM-like structure, and then we can apply XSL style sheets to particular nodes or to the entire DOM or really anything like that. It's pretty straightforward. If we go the XFA approach, it's very similar. You can do it basically the exact same way, and so either works perfectly for triggering bugs here. One thing I want to point out is one thing that you really want to do if you're doing any sort of parsing of XML documents is filter and only do certain things on certain nodes, and that's done through these select attributes using a syntax called XPath. The main thing about XPath is you have fairly rich syntax to specify individual nodes depending on their ancestors or siblings or anything like that, also their attributes. And to aid that, there are a lot of functions that are available to you that you can call to basically filter out different nodes. And the vulnerabilities we'll talk about are in the lang function, CVE 2012-1530, and the bypass is 2017-2962, both of which are type confusion. So the way the functions are handled for everything in the XPath syntax is there's a giant switch statement for every single function that it supports inside a function called callfunc. And when it goes to handle this, it ensures that it has the correct number of arguments. So for the lang function, it's responsible for filtering based on the localization of a particular node. And it does that by checking to see if that particular node has a lang attribute set to whatever language you're looking for. So if you want en-us and your node specifies en-us, then that would return true and it would be selected. If it doesn't, but its ancestor node does have that set, then that would be selected. And so basically, it'll iterate from the current node all the way up the ancestor chain and test repeatedly whether or not it even has a lang attribute, and if it does, if it equals what we're looking for. And so that's exactly what this code does. But if we look at the very, very bottom line, we'll see a call to a function, or what looks to be a function called 2e, on the current node that we're operating on, and then that gets dereferenced and function gets called as a result of it. If we look at what 2e actually looks like, we'll see that it's actually a macro. That macro is just calling another macro called cast. Cast is conditionally defined. The sad thing is, if you are looking at a debug build, then it's going to call dynamic cast. And if you do a dynamic cast of incompatible types, then it's just going to return a null pointer. And in this particular case, because we're already dereferencing it without checking anything, we'll end up crashing, but pretty innocuous. In the production code, that ends up being a C-style cast, and so we just trigger type confusion if we're providing a type that is not appropriate. Unfortunately, it is trivial to use a type that's not appropriate, and with this proof of concept, it'll end up crashing as it tries to dereference ABCD as a pointer. It's very, very straightforward here. We just have an XSL style sheet that will match on every node and then just call lang function on a given node. In this case, it will target ABCD, and you have an instant access violation. So Adobe patched this as they patch everything and fixed the crasher. It no longer crashes. Unfortunately for them, they didn't actually properly look for any variant testing whatsoever, and Agari found that he could bypass this patch with text nodes or comment nodes. And so here's an example, and in this case, he just merged the two together in a XFA, and in this case, we'll end up crashing as we dereference XXXXX. It's very, very simple and very, very straightforward to trigger, and Adobe just did not do any variant hunting. We can see how they actually patched it thanks to updated Sablotron sources that they provided. And we can see that they actually fixed it properly, but now actually using a call to dynamic cast. and there's a bill pointer check afterwards. And we know that it's in reference to the case that we submitted to them because we see fixed for PCert 6081, which is just kind of nice to be able to see. And with that, I'm going to hand it over to Abdul.
So I just want to note down that recently Adobe updated the sublotron code and uploaded it to their website, so you guys can check it out if you guys want to find more bugs. All right, so I'm going to talk about indexing, which is relatively a new attack surface. I found this last year, right before Ponto on, and it happens that Sebastian Appelt, which he was here probably, was looking at the same thing, but he was being a little bit quiet about the whole attack surface. So you can reach this through eScript, catalog, API, plugin, search plugin, and eventually everything that deals with index parsing happens inside Onyx 32. So what's Onyx 32? An overview. So basically, back in 2003, Adobe needed a solution for, like an indexing solution for fast searching in PDFs. So they bought a solution from a company called Lextech. They offer that, and it's called Onyx. And basically, it's just a DLL, Onyx 32.dll. And everything that deals with indexing, fast searching happens there. The nice thing about this is that this DLL hasn't been audited. So when I saw the DLL, it was the last time it was modified was 2015, I guess, or 2014, something like that. So no one touched it. I included a note here that it was possible to trigger the parsing code through JavaScript. I don't think it's possible anymore. I'll get to that later. The nice thing about Lextech, they provided documentation and sample code of how to use the actual API of Onyx. So what I did is basically I read the documentation, grabbed some sample code, I wrote a small harness, and I started fuzzing the DLL directly. And I found a bunch of bugs. Sebastian did the same thing, but he basically took another approach. He did WinAFL, I did my own framework. He found more bugs than I did, which is fine. I admit defeat. But I'm going to be discussing an interesting bug, which is an untrusted pointer dereference, which we both found. I found it first, so I can't live on that. But he bypassed the patch later, so it's an interesting use case. Okay, so initially I was approaching, I wasn't looking at indexing. I was looking at the catalog plugin, which is a plugin that only exists in Acrobat and not Reader, which is the paid version of Reader. So the way it works, you can grab a bunch of PDFs and create an index file for them for searching purposes. That's the whole purpose of catalog. So it generates a PDX file, which links to two files, a master index file and a slave index file. In this case, it's index and index1. I found out that you can pass the path of PDX, and then you can call build on it, and then you can force the triggering, the parsing to happen, the Onyx code. The thing that I want to note down is that build is not documented. So I found it by accident. It was just dumping shit out of catalog, and I found it, which is cool. Eventually, I was able to find two types of bugs. The first type of bugs affected the actual core APIs of Onyx, and the second type of bugs actually affected the way these APIs were being used inside catalog. So if you use them in a specific way, then you can trigger heap overflows in the catalog plugin. That said, I shipped, I think, 4 bugs, I think, 3 in catalog and 1 in the core APIs. Send them to Adobe, they went back to us with a fix, and they fixed, they basically had to send the Onyx bug to Lextech. They fixed it, they got back to us, and they disabled the build API. So basically, according to them, we cannot reach that code anymore. They went further, and they were like, listen, we're not interested in these indexing bugs anymore. And they sent us a big email listing all the possible vectors that they think that you might be able to use to reach that code base. And inside the email, they basically mentioned the search plugin. And they were like, listen, the catalog stuff is done. You might be able to reach it through search, but every single method in the search API is privileged. So basically, you guys cannot do it unless you bypass the privileges. So I was like, okay, but it happened before. We were able to bypass privileges, and we were kind of making that argument. In the meantime, I think like the day after or a couple of days later, Sebastian pings me, and he's like, well, I found a way to actually trigger all these bugs. And I was like, how? He's like, through the search plugin. I was like, no, Adobe said it cannot be done. And in fact, what he found out is that one of the methods, if you pass a specific argument to it, then you can hit it through the document privileges. So basically, Adobe didn't do their job quite well. So in fact, what he did, he used that, and we treated it as a bypass, mitigation bypass. And he slammed all these bugs together. So he eventually sent like 9 bugs or something. So Adobe eventually admitted defeat as well. And they started processing these cases. So back to the untrusted pointer dereference. So this was initially found by myself through fuzzing. And it was in IAX start retrieval session, which is exported by onyx32.dll. Basically, I called it an untrusted pointer dereference. Sebastian calls it an internal overflow, which is true because you overflow an object and basically overwrite a file class T pointer, which gets dereferenced later. The interesting part is that you can override that file class T pointer with a counter. Initially, I thought that I cannot control this bug. I did further investigation, and it turns out that you can increment this counter by duplicating a certain object inside the actual index file. So I started replicating this object, and I ended up with this like 10 megabyte of index file, like all replicated. And eventually, I was able to control it in something meaningful. We sent this back to Adobe, and basically, when they patched it, they sent it to Lexstack. When they patched it, Sebastian got back to me. He's like, I can trigger the bug again. I was like, fine, send me the crash. And it turns out that what they didn't fix the core issue. They added a simple magic value check. And basically, if you get that check right, then you can trigger the bug again. We sent that back to Adobe, and Adobe sent it back to Lexstack. Eventually, they got back to us, and they were like, listen, Lexstack is not going to patch this on time, right? I think they don't have the staff for that or whatever. And they figured out there's only one solution to it, which is basically kill the whole thing. So they disabled the whole Onyx code base. Basically, if you want to enable it, you have to do that through the registry key or whatever. So this is the indexing stuff. We're going to go over some file parsing issues. Brian's going to start off.
Yeah. So one of the kind of newest, hottest areas inside of Adobe Reader is file parsing vulnerabilities. And the way that it works is a lot of it's happening in image conversion, right? And so image conversion will actually take an image and try to convert it into a PDF for display within the application. And it's really nice because you can, again, reach a lot of the back-end DLLs where a lot of this older code is, including font parsing, JPEG 2000 parsing, et cetera, color management, graphics management, all of these different APIs that you wouldn't normally be able to get to. Now, the way that it works is that image conversion is a plugin that's actually used to convert those images to PDFs like I talked about. And it can be used, you can simply trigger it by opening the image file from within Reader, right? So it automatically go to image conversion and try to convert it. But you can also do it from JavaScript, right? So if you're trying to deliver a payload where the actual attack doesn't happen from opening it from within Reader, you can open it from JavaScript, right? And they actually leverage a lot of open source projects. And so you can actually use like AFL and some of these other tools and fuzz the actual open source components and then actually apply those bugs and try to trigger them from within inside of the closed source binary itself. Now you can see like we put some of the like stats for the types of bugs that we're getting in this area, and you see back in 2016, really nobody was looking at it publicly at least, and sending bugs to us. So just 2 out-of-bounds reads. But if you look in 2018, it really exploded, right? People are really fuzzing this hard, including some of the people in this room, and we're receiving a lot more bugs in this area, and a lot of the code is being audited quite heavily right now, which is interesting. Now, like I said, you can do EMF parsing, JPEG parsing, all of these, JPEG 2000, TIFF, et cetera. So there's a lot of formats to go fuzz if you're interested in. But one of the most buggy formats that we have seen in the program is actually EMF, right? So EMF can actually be parsed by Adobe Reader, and Abdul's going to cover all of the details related to EMF parsing and the bugs that we've seen there.
So one thing I want to mention that at one point of my life I was fuzzing Foxit Reader. So I was fuzzing the image conversion in Foxit Reader, and I got this crash in a JPEG image. So I was like, let me test it in Adobe, and basically it crashed as well. At one point as well, we were doing auditing on Adobe Reader, and we found a bunch of bugs in JavaScript. We tested them in Foxit, and they actually hit too. So you guys, if you guys have a bug here or there, you might get it to hit on the other software, just a note. Back to EMF, so basically it's a very old file format. Initially it's WMF, basically a 16-bit format back to Windows 3.11. And then it evolved when 32-bit GDI has been introduced, and basically it's now EMF. It's documented, it's all online. Most of the bugs that we got were in the records parsing, which I'm gonna get into. Basically, it has records, a bunch of records. Each record has a type, has a size, and a record buffer, a bitmap record buffer. The buffer has a bunch of parameters, but we're not gonna get into that in detail. So this is the record that we've been getting a lot of bugs in, which is the alpha blend, which is basically specifies a block transfer from the source bitmap to a destination rectangle. So the bugs that we receive basically affect the way the parsing happens. So before the application attempt, so before the parsing happens, it allocates a buffer, and then it tries to copy a bunch of data to it, and then it allocates another buffer and tries to move it up to the initial buffer. In a nutshell, let me show you the code flow from a high level. So initially, it starts off with parsing a bunch of EMF fields. Then it allocates a buffer, right? Then it chooses the compression. Based on that, then it goes to a parsing function, a bitmap parsing function. In that parsing function, there's a switch case based on the bit count. In these switch cases, it allocates another temporary buffer. Then it puts bitmap data in it, then it enters a copy loop, and it copies it to the initial buffer there, which is quite innocent, but Adobe managed to massacre the whole thing. So first bug that I'm going to be talking about is a heap buffer overflow. Let's go back to the flow. So it starts parsing a bunch of EMF fields, which I've highlighted here. These are the ones that are relevant to this bug. It allocates the buffer based on the following formula, which is X source multiplied by 3 or 4, based on the value of bit count. So if bit count is 18, then it multiplies it by 3. If not, multiplies it by 4. Can you guys see the bug? Yeah, I think so. So basically, if you consider the following values, 55556 multiplied by 3, then it's going to wrap. It's going to end up in a size 2 buffer, and basically kind of integer overflow. The compression that we used in this case is RGB. So basically in Acrobat, it supports the following compressions: RGB, RL8, RL9, and bit fields, which are in one switch case. The bugs that I'm going to be covering basically covers the first compression, which is RGB. So when the parsing happens, we overflowed the buffer, the integer, and then we go to the switch case based on the bit count, allocate a buffer, get the bitmap, and then enter the copy loop. In the copy loop, the counter is CX source, which is something we control, and basically we overflow buffer, which is pretty simple. So this is the first allocation that happens there. As for the patch, I don't think they actually understood where the bug is. So something I did not mention, before the allocation happens, there's a small multiplication that's done. It multiplies b width by b height multiplied by 3 or 4. It's not a check for integer overflow. It's basically a check whether it exceeds a certain size for allocation, basically. If it exceeds a certain size, then it's going to tell you not enough memory. If not, then go ahead. So what they did, they thought that b height is the problem. So they entered another check. So basically it fails because if you consider the following, if b height is 1, then basically it's going to bypass that check, and it's going to allocate exactly the same way it allocated before. So what they did, they basically just made sure that the puck that we send them does not hit, right? Regardless of whether what you guys control and what you guys do not control. So I'm not going to go over the final fix because they basically fixed both bugs that I'm going to be talking about in one fix, which we're going to mention later. So the last bug that I'm going to be talking about is an out-of-bound read. Going back to the code flow, it allocates the buffer. This time we're not going to overflow that buffer. We're not going to trigger the bug. Choose the compression. This time the bit count is 20, and then we allocate a temporary buffer. The temporary buffer is allocated using this formula, which is basically bit count multiplied by width shifted by 3. And if you guys consider these values, And it's 20 multiplied by 80001, divided by 3, and then it's going to overflow, and you're going to end up with a buffer of size 4. So basically, they failed every allocation here. Then you basically enter a copy loop. The copy loop is based on the X source counter, and then you're going to trigger an out-of-bound read when accessing that temporary buffer. So how did they fix this guy? So they went back 5 calls, all the way back, because they figured they have to fix it from the root calls, right? And in this case, I think it was the same developer. He basically thought that 7FFFF is the value that we should look for. And he just wanted to make sure that the value is less than 7FFF. In fact, this is the comparison here. So in fact, if you consider the following values, because we control all the values, right? 4 multiplied by 40002, shifted by 3, then you're going to have a small buffer as well. And then you're going to trigger the bug again. So I mentioned that all these bugs exist in the RGB compression, which is the first case. Nevertheless, we did a little bit of investigation. It turns out that case 0 and case 3, the functions, are almost identical, with a slight change in case 3. So basically, all the bugs that you can trigger in case 0, which is compression RGB, can be actually triggered, the same exact bugs in the other function, which is fascinating. So that said, we sent all this to Adobe, and they basically figured out that there's only one way to fix it. Kill the whole thing. Yes. So basically, they disabled EMF parsing, and you can enable it through the registry. They also, I think they killed XPS parsing because they got hit really bad as well. So that's basically it. I'll give it to Brian to conclude.
Yeah, so in conclusion, I mean, obviously we're having lots of fun at the expense of Adobe, but you know, we wanted to, like, in reality, what we really did is only covered like 4 pieces of the attack surface, right, that are interesting, right? So if we look back at the general architecture, the real question that we have is like, what exactly is going on in that code base, right? So we want to, you know, if we're seeing the same bugs over and over again, where are we seeing regressions happen? When are the regressions happening? How fast are they discovered? Which means how fast can an attacker take advantage of just basically patch diffing the bug and finding the bypass, right? There's an entire industry out there just for generating end-day POCs, right? So if you look and they spend a little bit more time just looking at Adobe stuff, you'll be able to get into the industry of the 0-day POC. So that's, you know, it's kind of interesting. So if we actually go back and highlight all of the pieces of the attack surface where we've had regressions occur, it gets basically all red, right? So you know, when we're looking at the code base and we're spending a lot of time analyzing the components, you know, it's showing up over and over and over again. Now you have to understand, like, the big software manufacturer having 4 months to patch a bug, you know, lots of pressure, a lot of, you know, bugs coming in. It is actually a challenge. And so, like, if we look at the final thoughts, I like to kind of separate them between defensive and offensive perspectives, just because it's, you know, we're at OffensiveCon, so we're going to look at the offensive side. But patching can be very, very challenging, right? So not only, like, us in the security world, like, we live and breathe all of these different vulnerability types. We spend a lot of time looking at the code base. You can imagine a sustaining engineer who gets the bug from their security app mailbox has to go in and analyze all this stuff, and like they're getting lots of different bugs. And so trying to fully understand all the proof of concepts, it can be really challenging for them because they may not be as passionate about the code base as we are, right? But in this case, you know, we're poking at Adobe, we're making fun of Adobe a little bit, having some fun with them, but Adobe's not the only vendor struggling with this, right? There's a lot of failed patches coming out. In fact, Patch Tuesday was, what, this week? And we're already aware of failed patches in the Microsoft patches that occurred, right? So it's happening across the industry. And if you look at the other verticals, like we're talking about Adobe and kind of these big name vendors, but if you look at the other verticals like SCADA and IIoT, there's a significant amount of failed patching going on. And we'll be talking about that later in the year, more than likely, where there's so much failure going on when it relates to patches that it could almost be considered fraud, right? So, you know, looking at, and a lot of what the vendors are doing is, you know, eliminating those old code bases. They're not even going and fixing the bugs anymore. They're just saying, like, forget it. We're just going to disable the entire thing. You know, nobody's using this code base. We're just going to get rid of the whole thing. You know, which is a viable solution, and maybe the only viable solution if you don't have access to the code or the developers have left, and if you're not interested in supporting that stuff. You know, make it a really painful on the end user to actually go use some of that functionality that they're trying to get access to. Now, from the offensive perspective, obviously patch diffing is going to be extremely valuable when you're dealing with code bases where you know failed patches are occurring quite often. And you can use that to go find new variants, like, for example, the proof of concept that Jazel talked about at the very beginning of the presentation where they didn't fix it in the else clause, right? You can do a patch diff and go look in the else clause, right? Even Project Zero missed that one. So I know, like, when we were doing the proof of concepts, you wanted to mention the closed doc thing.
So Brian had shown that basically just replacing app.closeDoc with exec menu item close was sufficient to trigger a bug. There was one that I wanted to bring up then and I didn't remember until a couple slides later, but Abdul found a bypass where it was just calling closeDoc twice to now trigger the use after free. And that's just ridiculous.
Yeah. So you just, spending a lot of time looking at the proof of concepts that exist out there, doing simple modifications or inexpensive modifications can actually extend the life of the exploit. Like if we look at the EMF one, there's like 15 different ways to hit the different bugs just underneath in that one piece of code, right? So there's ways that you can go about and extend the life of the proof of concepts that you have, or re-trigger them and get paid twice by bounty programs like ours, just by understanding what's being patched, how it's being patched, and always remember 7FFF is the god of all evil, at least for Adobe. With that, is there any questions? I can't see you because the lights are so bright.
Everybody hungry?
Yeah.
Okay.
Thank you very much. I want to thank OffensiveCon for having us out here. We sponsor it every year, so it's a great conference.
Thank you.